Video number 128 plus. Small astronomical calculations. Hello. What I'm going to talk about today could have been included in video number 127 plus, dedicated to hypotheses about antimatter. But that would have weighed down the discussion and perhaps discouraged some listeners. In video number 40 plus, I reminded about the importance of orders of magnitude, often associated with powers of 10, to understand the relative importance of the factors involved in a physical phenomenon. In astronomy, and even more so in cosmology, this notion conditions the understanding of phenomena. Calculation number 1. What is the ratio between the average diameter of a star and the distance between two neighboring stars in the galaxy? Answer. The Sun is an average star, and the order of magnitude of its diameter is about 1 million kilometers. Two neighboring stars are a few light years apart, and a light year is about 10 trillion kilometers. The ratio between the two is therefore of the order of 10 million, or 10 to the power 7 if we represent a star by a marble or a grape. Its nearest neighbor will be a few tens of millions of centimeters away, that is, a few hundred kilometers. Calculation number 2. What is the ratio of the galaxy's volume to that occupied by the matter of the stars? Answer. The image we have of a galaxy from photos where the stars seem almost contiguous because they shine so brightly is completely false. The volume of the galaxy is approximately 10 to the power 7 to the cube equal 10 to the power 21, which is 1,000 billion times the volume occupied by the matter of the stars. In comparison, 1 liter of air contains about 2 times 10 to the power 23 molecules, whose individual volume is of the order of 10 to the power minus 30 meter cube, or 10 to the power minus 27 cubic decimeters, and the total volume is 2 times 10 to the power minus 4 liters, so the volume of air is just a few thousand times that of the molecules, which are incomparably denser than the stars. The matter of a galaxy is much more rarefied than that of our terrestrial gases. Calculation number 3. If our galaxy collides with an identical galaxy, can we estimate the number of collisions between stars during the encounter? Answer. Let's see what would happen during a face-to-face encounter, as it would be roughly the same order of magnitude in other cases. Each star must therefore cross the thickness of the other galaxy, of the order of 1,000 light-years on average. For each slice of a million kilometers, average diameter of a star, it has a 1 in 10 power 14 chance, surface ratio, of encountering another star. And since 1,000 light-years is 10 billion kilometers, you need to multiply 10 power minus 14 by 10 billion equal 10 to the power 10 to get the probability of a collision. The result being 10 power minus 4, we conclude that about one star out of 10,000 will undergo a collision. Why is this calculation interesting? In connection with the previous video, I wondered if the collision of a galaxy with an anti-galaxy could be distinguished from a collision of two ordinary galaxies at a large distance. The result of the calculation shows that it will be very difficult, the loss of luminosity being negligible. On the other hand, the gamma ray burst caused by matter-antimatter annihilation also seemed too few to be detected during an observation period of the collision limited to a few years. The other interesting question is whether gravity can cause the annihilation of a star with a possible anti-star from the galaxy or a galaxy with an anti-galaxy. For this, it is enough to compare the gravitational acceleration evaluated in meter per square second between these two objects with their distance in meters. The time of collision by gravitational attraction is about the square root of this ratio. Of course, the acceleration changes with the approach, but for example, we can already see the time needed to halve the distance, knowing that on the journey, the acceleration is less than 4 times initial value. Case of stars. Let's reason in relative values, knowing the Earth's surface acceleration of 10 meters per square second and the Earth's radius of 6,000 kilometers. An average star weighs about 300,000 Earth masses. That multiplies the acceleration by that factor. For a very close star located at 0.6 light years or 6 trillion kilometers, the distance is 1 billion times larger. As it is the square of the distance that counts, we must divide 3 billion meters per square second by 1 billion billion, which gives 3 out of a trillion. The order of magnitude is therefore 10 power minus 12 meters per square second, knowing that stars are generally much more distant. The distance in meters being of the order of 10 power 16, we find the time of the order of 10 power 14 years, which is of the order of 10,000 times the supposed age of the universe. Case of galaxies. Let's compare with the calculation we just did. A galaxy contains 100 billion equal 10 power 11 stars, and the ratio of distances is approximately 10 power 6. So capital M divided by d square is 10 times smaller, and the order of magnitude of the acceleration is 10 to the power minus 13 meters per square second. The distance in meters being on the order of 10 power 22, we find the time on the order of 10 power 17 years, which is more than 1,000,000 times the supposed age of the universe. The galaxies will be dead long before. Conclusion. The penultimate calculation shows that gravity will have almost no influence on collisions between stars, as we implicitly assume in calculation number 3. Finally, even if antimatter is equally distributed with matter in the cosmos, the two will stay quietly in their own place, and if collisions happen, we will probably have no way to know it.